Okay. Hello, hello. Good day. Currently, it is good evening for me. Uh, my goal for today with this recording is to just guide you guys with our answer key for the diagnostic examination, for a diagnostic assessment that I gave you guys yesterday. So that was yesterday at the time of the recording. I'm currently a bit sick, so forgive me. This is not how my voice is supposed to sound like normally, but anyway, let's begin. Right? Let's begin with multiple choice. Select the best, most correct answer by writing down the letter of the choice corresponding to your answer inside the box provided to the left of each question. Let's begin. Number one. Which of the following details does not apply to reversed cycles as opposed to power cycles? So what we mean to say, or what the question is asking, is what applies to power cycles, right? What applies to power cycles? And if you're a bit confused by that wording, well, the way to make this work, kumbaga, the way to make this question work is to spot the odd one out, right? Everything in here except for one thing applies to something. And as you will see, right, letter A, in schematics, the flow is counterclockwise. The distinction between power cycles and reversed cycles is that, if you did not know, right, normally power cycles, if you put them in diagrams, like let's say, for example, a TV diagram or PV diagram or whatever, or TS diagram, power cycles always have a clockwise rotation, right? Let's say, for example, your cycle looks like this. If it's a power cycle, the states will go from here to here to here to here. As you can see, that follows a clockwise motion. And if you reverse everything, that is where you will get a reversed cycle, right? So this is for reversed cycles, all right? This is for reversed cycles. Heat is supplied to achieve some work. That sounds like what a power cycle would do, right? We give the power cycle heat, it gives us some work or some electricity, if you want to think about it that way. Letter C, work is supplied to transfer heat. This is exactly what a reversed cycle does. So honestly, we can stop there and we can write down letter B as our answer. Thing about this is that if you want to be really sure, letter D, measured using coefficients of performance, very, very obvious na ito, right? This is very obviously for reversed cycles. So, for power cycles, letter B ang ating answer. Now for number two, the thing about number two is that I kind of meant to give this out as a as a bonus question, kind of, more in the sense that, well, there are two answers that I would think fit this description, right? Which of the following steady flow devices is not commonly used in reversed cycles? When I was thinking about this, I was not thinking about other reversed cycles. I was mainly thinking of, and I should have written down, the vapor compression cycle, right? And the thing about this is that also, partially, I was also thinking about other reversed cycles. Let's say, for example, the reversed Brayton cycle or the air cycle, right? The air, reversed. Basta, it's a cycle that uses air as its working fluid. And the thing about that is that in the vapor compression cycle, we have a compressor, a condenser, an expansion valve, and an evaporator, right? No boilers, no turbines. Excuse me. And in a Brayton cycle, a reversed Brayton cycle, it has condensers, compressors, turbines, and evaporators. You don't use boilers. But also, there is another kind of refrigeration system, if you guys spotted that, which is the steam jet refrigeration system. And the thing is, how do you make steam? Well, you use a boiler. And honestly, I will accept these two as answers, right? You won't see necessarily boilers or turbines in the common, right? In the common types of reversed cycles, right? Because for these two, sadly, or well, not sadly, but they are most usually seen in a lot of reversed cycles, right? So I will accept either of those answers. Number three, A heat pump operating as a refrigerator, that's a very good word, refrigerator, operates between, what is happening? There you go. Operates between 20 degrees Celsius and 80 degrees Celsius, right? So those are numbers, very interesting numbers. And very interesting numbers. What is its highest possible coefficient of performance? Highest possible COP in this case refers to the COP of the Carnot cycle with temperature limits of 20 and 80, right? So very basically, for number 3, your solution should have been something like TL is equal to the low side, which is 20 degrees Celsius, and your high side is 80 degrees Celsius. Just to check if I am recording. Anyway, right? This is what you should have done. And the thing is, if you have forgotten the COP formula, well, poor you, right? But the COP formula is going to be for the Carnot cycle, reversed Carnot cycle, it's going to be TL all over TH minus TL, right? The thing about this is that you could have written this down as 20 over 80 minus 20. Your answer here would have been 0.333, which is not very good. Not only is it not very good, it's wrong, right? I put this here, right? Because I want people to think, I got the correct answer. When, in fact, the correct answer should be, it's very close to this one, right? Okay, yeah. When in fact, the right answer is very close to this one. The thing about this is that you should think about these temperatures as absolute. And the thing about this is that your 20 is not just 20 degrees Celsius. It should be in terms of Kelvin, which means you should add here a 273.15. This would actually give you, let's see, 20 plus 273.15 divided by 80 minus 20, that is going to be 4.8858 or 4.886, right? 4.886. That is your number 3. All right, number 4. So very hard if you did not have your calculator with you. I'm so sorry for that. Right? But number 4, a hollow steel cylinder has an outside diameter of 20 centimeters and a length of 60 centimeters. If we know that the steel lining is 1.5 cm thick all around, that's a very good, that's a very important keyword pala. How much empty space is inside the cylinder? Right? And you might think about this, you might say, that this is no big deal. Right? This is not very difficult because, well, it's just literally a volume of a cylinder problem. But the thing about this is that you might want to think just twice. Might want to think twice about this because, well, let's say, for example, the outside diameter and length are 20 and 60. Let's try and draw this thing. Yan. And then, let's just copy this. Copy, paste. Paste it here. Okay. Like this. Like this. Okay. Let's say, for example, the outside diameter is 20. The thing about this 20 value is that we are not looking for 20. Instead, we are asking the empty space, right? How much empty space is there inside the cylinder? The thing about it is that there is a steel lining and this is an outside diameter. That means that there is a steel lining of 1.5 each side. So the inside diameter, the actual empty space that you should encounter will be 20 minus 1.5 minus another 1.5. That is going to be 17. That's the actual value you should use as your diameter. And not only is that the thing that you should subtract from, this 60 over here is also misleading in the sense that, well, 60 is not really just 60 because, again, there's a steel lining. There's 1.5 and another 1.5 here that will cause you to, again, subtract two 1.5s or just a 3. which means instead of 60, you should use 57. And from there, everything should be good as long as you have a calculator, right? The volume of a cylinder is pi r squared height, or the big boy version, pi over 4 d squared times height. And the thing about this as well, something I teach to my students is something called mise en place, right? If you're already detecting that there are units that you don't want to use, let's say, for example, let's say, for example, centimeters, you might already want to think about converting them in your head before you even write it down. Like, let's say, for example, instead of writing it down here as cm, already just do it in your head, right? Pi over 4. D squared natin would be 17 cm, or 0.17 meters squared. And then for height, instead of 57 centimeters, we do 0.57. And the thing about this now is that you will see that the units should be in meter cubed. But what we want is in liters, right? So let's just convert, right? What do we convert into? Well, we can convert directly, right? 1 cubic meter should be equal to 1,000 liters. Cancel, cancel. Now, we can put this in our calculator. 0.25 pi times 0.17 squared. Squared times 0.57 times 1,000. That will give us 12.937 or 12.94 liters. Right? That is our answer. Letter A. Okay, there you go. Now, number 5. Which of the following refrigerants is no longer widely used? The thing about this now is that, well, you guys kind of have an unfair advantage, because I already told you that one of the refrigerants we use normally would be air. So this is not the answer, right? And now, if we think about it, well, there are 3 other things. There are 3 other options. And the thing about this now is that if you don't know anything about, well, legislation regarding refrigerants and what should not be used anymore, right? At the very least, you should be somewhat familiar about, well, aerosols. Let's say, for example, the things they put in hairspray before, right? They used to tear up holes in the ozone layer, right? And also refrigerants do that sort of thing as well. And hopefully you have heard of CFCs, chlorofluorocarbons, right? And maybe HFCs as well, hydrofluorocarbons, and chlorohydrofluorocarbons as well, CHFCs. And the thing about that is that, well, what is in here? What substance is in here that has a fluorine or a chlorine or both? That is letter B. This is R22. Actually, for the tables that we will use for this subject, we will be talking about mainly refrigerants that are no longer used. That's how old the textbook is, right? R22, R11, R12, all of them are phased out. Currently, we are trying to use better refrigerants, or fluids that will not tear holes in our ozone layer. But, well, what's supposed to not be here any longer is R22, right? That's letter B. Letter A, Letter A, you actually use ammonia still. But that's very dangerous in and of itself. It's not dangerous because it's poisonous, although, of course, everything can be poisonous with enough of a dose. It's just that sometimes it explodes, right? And letter C, same thing. This is butane, actually, C4H10, right? More specifically, isobutane. If, I don't know if lucky is the correct word, but if you look inside your refrigerator, if it still has that sticker at the back of your refrigerator, as in like if you open it up, like if you open the door and then you look at the back, there should be a sticker there with with details, what kind of refrigerant it uses, right? How much refrigerant is currently circulating in your refrigerator, and actually air conditioners do this as well. You may find that the thing they use to circulate, basta to conduct the refrigeration is isobutane. So you may be using this as well, right? The only thing that should no longer be used is R22. Okay. Now, number 6. The thing about this is that you guys have an unfair advantage because you have calculators. Number 6 should be very easy, so long as you know the difference between letters A and B and letters C and D. Letters A and B, of course, are the degrees Celsius and degrees Fahrenheit scales. Yes, we know them. But they are hot, right? They are hot with regards to the absolute temperature scale, right? We know that the boiling point, or rather the freezing point of water is 0 degrees Celsius, but it's actually, right, 0 degrees Celsius, but it's actually equal to 273.15 Kelvin, right? They have the same scale, C Celsius, C degrees Celsius, and C Kelvin. That means that you are just stepping back. That means that the lowest possible temperature that you can attain is 0 Kelvin, or negative 273.15 degrees Celsius, right? And the thing about this is that degrees Fahrenheit also has this kind of thing, right? For degrees Fahrenheit naman, the freezing point of water is 32 degrees Fahrenheit. And now if you turn that into degrees Rankine, the absolute version of the Fahrenheit scale, right, it will be 459.67 degrees Rankine, right? Therefore, the coldest possible temperature would be 0 degrees Rankine, or of course negative 459.67 degrees Celsius. Fahrenheit. And the thing about this is that these two are equal. Right? They are equal. That means that, well, this is a kind of equalizer, of course, because they're equal. This is an equalizer, right? 0 Kelvin, not degrees Kelvin, but 0 Kelvin is equal to 0 degrees Rankine. And as we know from the Celsius and Fahrenheit scale, right? From 0, it takes up to 100 degrees Celsius for us to boil water. But for the Fahrenheit scale, it takes us up to 212, right? And basically, the difference between these two is 180 degrees. And the difference between 100 and 0, of course, is 100 degrees. That means that 1 degree Celsius difference ito, this is a temperature difference, not a temperature reading, is equal to 1.8 degrees, Fahrenheit difference in reading. When we're talking about temperature differences, then they make the same kind of sense if we're talking about the absolute scale. That means 1 Kelvin is equal to 1.8 degrees Rankine. And therefore, you can see that if you turn 24 degrees Rankine into Kelvin, you can just say that this is going to be 13.3 Kelvin. That means that this is the lowest possible temperature that we can get, right? Because clearly, these two are way too hot, right? Ang totoong labanan lang is between letters C and D, which means letter D is our answer. Number 7, in an actual thermodynamic cycle TS diagram. So this is a reminder for you to just brush up on your method 2. Why do vertical lines always lean to the right? Right? The thing about this is that we are talking about actual thermodynamic cycles, right? We're talking about actual, not actual. And the thing about a TS diagram is that when you're talking about a TS diagram, the T is the y-axis and the S is the x-axis. What do they mean when vertical lines always lean to the right? This is a vertical line. This represents what we're supposed to see as isentropic. But in real life, actually, processes look like this. Why? right? This is our ideal, and then this is our actual. Why is that? Because, of course, the second law of thermodynamics always tells us that, look at this, the initial entropy and the final entropy of this state, right, is going to increase, right? This is supposed to be what happens, right? In TS diagrams for thermodynamic cycles, this is for an isentropic, quote unquote, isentropic process. But that does not happen because always, entropy increases. And if you try to think, or if you think about letters A or letters A or D, excuse me, the thing about them is that, yeah, they are correct, but they are not the best answer. In this case, they are consequences of the fact that your entropy always increases. That means that number 7 is letter C. Number 8, in a reversible Carnot cycle operating between TH and TL, T high and T low, which of the equations are true? This is actually something we saw earlier. The thing is, all of these equations refer to the same thing on the right hand side, high over high minus low. Earlier, we were talking about low over high minus low. And so that means that we are not talking about cooling, the cooling part of the COP. We are talking about the heating part of the COP, also what we call the performance factor. That means that number 8 is letter B. Number 9, which of the following aspects are not important when choosing suitable refrigerants in HVAC systems? Now, the thing about this is that I will tell you right now, the answer is not letters A, B, or D. Right? Some people answered letter D, which means I'm so sorry. Like, why would you not choose something that is? Why would you choose something that is toxic? Right? The answer is letter C, miscibility with condensate water. Last time or yesterday, I told you guys that the word miscibility means mixability, right? If it's, for example, water is miscible with orange juice, something like that, right? That means that you can mix water and orange juice and have them be in one continuous phase, right? But water is immiscible with oil because even if you mix them together, they will settle into two different liquid phases. The thing about refrigerants is that, well, they will come into contact supposedly only on the inside, in the inside of your refrigeration cycle. But of course, we're dealing with things in real life. Sometimes, right? Bad things happen. And of course, we want it to be environmentally friendly. This is why we phased out R22 and all of its other friends as HCFs or, HFCs or CFCs, whatever, right? We want it to be safe for us, right? That's why refrigerants, air or water as refrigerants sounds really cool because, well, that's pretty healthy. And the thing now is that the other thing that's important is because you don't want to mix your refrigerant with the compressor oil. Basically, the compressor is one of the most, if not the most important part of any refrigeration system. And for a compressor to work, because most of the time it has moving parts, you need to lubricate those parts. And what happens if things go wrong is that sometimes your refrigerants can leak. Sometimes there will be holes. And sometimes, and in those times, you do not want your refrigerant to mix with your compressor oil because what will happen is that the compressor, the inside of the compressor, is very sensitive. Right? The same way that a turbine is very sensitive when it comes to admitting small droplets of liquid. Right? It can't handle small drops of liquid. It will get damaged. Same way in here, if refrigerants mix with compressor oil, then they might bring in the oil inside of the cycle. And well, it's gonna wreck your moving parts. Right? So, well, the thing that does not that is not of concern for us would be letter C. Miscibility with condensate water. It's okay if it mixes in, I suppose, maybe unless you're like throwing the water out into a river or something, maybe, right? But that's not as big an issue as letters A, B, and D. Now, last, number 10, correct the following statement. All refrigeration systems use a kind of fluid mover to impart work in a fluid to reject heat from a low pressure environment to high pressure surroundings. Right? All right. Now, letter A, not all refrigeration systems impart work. Letter B, work is imparted to the system, not the fluid. Letter C, heat is rejected from high to low pressure. Letter D, this statement contains no errors. The thing about these kinds of statements is that you should always be looking out for absolute words. All, never, always, right? Those kinds of things, because they might be the kinds of words that invite parang fringe cases, right? Things that are not always true. And in this case, the answer would be letter A. Not all refrigeration systems impart work. What does this mean? Basically, diba, sinasabi natin for a power cycle, right? In a power cycle, what you're supposed to do is that you give it you give it heat, pala rather. You give it heat, it does its thing, it rejects some of that heat, but in the process, you gain your electricity or your work, right? So that's what's supposed to happen in power cycles. And what we're being taught now, or what we were taught before, is that reversed cycles, you need to give it work, right? You need to give it work in for you to enact some kind of weird process. Either you want to make something colder or you want to make something hotter, right? Ikaw na bahala. Most likely in the Philippines, it's the cooling that we want, right? So that's the thing that we are taught. Oops, Q absorbed. The thing about this is that as I'll be able to teach you guys the last topic that will have absorption refrigeration, that has no compressor, right? If anything, the compressor will not be responsible for being the one to facilitate the heat transfer out to its surroundings, more in the case of something else, right? It's actually a boiler, or well, we'll find out. You guys will find out soon, right? It actually requires heat. So if you think about it, you need to heat something to cool something. So that's a weird thing, right? But the thing about it is that absorption refrigeration systems work that way, right? Without spoiling too much, I mean, you can search it online, right? Absorption systems, what they do is that you mix in your refrigerant with something else and then heat that mixture up to drive the refrigerant into a higher pressure, right? It does not need work, it needs heat. So in this case, the thing that gives this away is the all, right? All. Because not all refrigeration systems use kind of a fluid mover to impart work in a fluid. Number 10, letter A. So that is our multiple choice. We'll now be moving on to the problem solving, right? So the problem solving, as you have seen, right, it consists of 10 points. 6 will go into this problem and 4 will go into another problem. Right? So if you want to get some water, you want to go to the bathroom, that's fine, right? Now, we will be back, right? You guys will be back. I will start solving this now, right? Problem solving. Solve the following problems and write down your answers in the boxes provided, unless specified, answer to 2 decimal places. Include the units of your answer whenever applicable. Please do read this. I have checked some people who did not include their units. You may use your questionnaire for your solutions because I did not ask you guys to bring a test booklet. Answers without explanations or solutions will not be credited. Partial credit is only applicable for legible, understandable solutions that are clearly labeled with the question number. Excuse me. Let's begin. Number 11. A throttling valve is responsible for bringing condensate from the condenser back to the evaporator of a vapor compression system. Basically, this valve is, if you want to look at the back of your refrigerator, it's a capillary tube. Basically, if you have one of those very old refrigerators with like the copper coils at the back, you will see that the copper coils get smaller near the end, near the bottom, right? That is your throttling valve. One of those things is, one of the types of throttling valves is a capillary tube. But basically, this is what we're talking about. And I've given here a very important clue. This steady flow device is isenthalpic, right? I was thinking whether or not to include this, but I'm pretty sure that I need to include this for you guys to actually solve this, right? The thing is that the steady flow device is isenthalpic, meaning that the enthalpy, that the enthalpy will remain constant, right? That's the important bit here. A throttling valve carrying water from a condenser with a pressure of PC is equal to 361.3 kPa, that one, to the evaporator with a pressure of 70.14 kPa. Oh, a throttling device carrying water from a condenser. Oh my gosh, I have a grammar error. Ooh, I should have included here. A throttling valve is carrying water. Anyway, what is the quality of the fluid as it enters the evaporator to 4 decimal places? Refer to the abridged property table of water below. And I didn't want to make you guys bring the steam tables, or else like you would have clued in that there would be a diagnostic assessment. So I just stuck this in here, right? Very, very focused. The thing about this now is that, well, we might want to make a diagram. Right? Number 11, there's this device. There's this valve, apparently. Right? There's this valve, and apparently it's supposed to bring water, right? It's supposed to bring water from a condenser with a pressure of PC, blah, 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 blah. Some people clued in that, of course, you should use the second row, but they were not sure what enthalpy to use, right? And because we are talking about a throttling valve carrying water from a condenser, what's supposed to come out of the condenser is already condensed, aka it should be water, aka you should use HF. The H for this should have been, right? The H for this should have been 589.13. And the thing about this is that because it's isenthalpic, the second state should also have 589.13. But now the pressure of the first state is 361.3. Now the pressure of the second state is 70.14. This is the main function of a throttling valve, is to reduce pressure, right? As you can see, 361 down to 70, right? And so the thing about this is that it reduces pressure in such a way that it retains all of the energy. That means that some of the energy that comes into here will, let's say, be split, right? If all of this were water, then at a lower pressure, some of the water will have become steam, right? So what is that quality? Right? The quality in here is that, well, H2 is the same as H1, but now you're in the realm of the first row. And the thing now is that that first row has an HF of 376.92 and an HG of 2660.1. And that means very easily we can calculate the quality of state 2 by using this formula, H2 minus HF over HG minus HF. If you did not remember this formula, well, now is your time to try and remember again, right? 589.13 minus 376.2 all over 2660.1 minus 376.2. This will give you your answer of 0.0929. I think that's the correct answer. I've been checking since yesterday. Okay, that is your answer. X2 equals 0.0929. All right. Number 12, continuing with the throttling valve in question 11, the volume flow rate of the water flowing from the condenser was found to be 0.45 liters per second. What would be the volume flow rate of the fluid flowing towards the evaporator in liters per second? Now, a lot of people have answered here 0.00 something, blah, blah, blah. Now, if you think about it, why? Right? That means that each second, such a small amount of water or steam will come through. Why? Right? If the volume flow rate of this is purely water in the beginning, then of course, right, your answer would be somewhat kind of similar-ish, right? But the thing is, there's steam in here, so now the volume expands. We'll see, right? The thing that should be conserved between state 1 and state 2 is not volume, but mass, right? So that means we should get the volume flow rate here, which is, 0.45 liters per second, right? And we should also get the volume, specific volume at state 1, which is going to be this state VF, 1.0797 liter per kilogram. Now, this should have been meter cube per kilogram, and then, this should have been VF times 10 raised to 3. If you guys remember, the thing is, when you are using your steam tables, you should always be doubly careful when you're getting VF. VF is the only thing in the tables that you should look out for, because you have to either divide or multiply by 1,000. I think it's only just divide by 1,000, right? But in this case, I've decided to spare you that extra step by writing down that the unit of this is liter per kilogram, right? And if you guys remember, the difference between a big letter and a small letter, right? A big letter is just going to be its corresponding M times small letter. So for us to get our M dot, we will just divide these two. We will get 0.45 liters per second all over 1.0797 liters per kilogram. And of course, we will see here that our unit will be in kilograms per second, which is correct, right? This means that this is our M dot. Let me just get our M dot. That is going to be 0.41678. So let's just say 0.4168 kilograms per second, right? Now, okay, what will we do? We want to get the volume flow rate of the liquid, of the fluid the fluid flowing towards the evaporator, aka what is now your V/2. And then very, very clearly, what we just need to do is just M, or M dot, times the specific volume at state 2. But the thing is, you don't know it, right? You don't know it yet. But we can try and know, because V2 functions the same way as U2, H2, and S2, in the sense that you can just write this down as M dot times, right, VF plus X2 times VG minus VF. Right? The thing about this is that we already know the values of VF and VG because they are very directly here. Right? We just have to fill out the correct ones, and we have to be very careful because these two are not of the same units. If we want to be very expedient, if we want to be very quick about this, let's just look at what units I'm looking for. I'm looking for liters per second. Okay. So that means this is more useful than this. That means that for me, I'm going to have to just make a conversion factor for VG. I'll write down everything in VF as is. right? So VF is going to be 0.4168 is our M dot. VF is 1 point, what is that again? 0360. So 1.036 plus X2 is going to be 0.0929 times VG. Your VG is 2.3610. 2.361, oops, 10 minus, right, 1.036. If you do this, you'll be wrong. Because again, this thing is supposed to be in meter cubed per kilogram. We need to turn it into liter per kilogram. And that means that this should be multiplied by 1,000 liters per cubic meter. So instead of this being a comma, instead of this being a dot, this should be actually a comma. 2,361, right? And now if we compute this, we should get, let's see, 0.4168 times 1.036 plus 0.0929 times 2361. 2361 minus 1.036. We will get 91.81. Wait a second. Let me see if that matches my answer. Yeah, I'm out. My answer here is actually 91.85, but that's because I did not round off the 0.4168. Let me try and see if I can make that pop out. Okay, you know what? Yeah, this works generally, right? 91.81. That is now our answer. 91.81 liters per second. And if you want to verify the units, go ahead, of course, right? But to tell you how it's done, right? Your M your M dot should be in kilogram per second, right? Your VF should be in liter per kilogram, and then this VG or this X2 is unitless. This is a ratio, right? This VG, which was supposed to be in meter cube per kilogram, we changed that into liters. So, as you can see, cancel. Liters per second. That is my number 12. That is our number 12, 91.81. 91.81 liters per second. Number 13, if all of the given information in questions 11 and 12 still apply, how much entropy was produced in this throttling process? Right? I told you guys as a kind of a hint already that 13 is a small value. Okay? Is a small value. And how do we know how much entropy was produced? Well, we just have to find out how much entropy was in state 1 and how much entropy was in state 2. Hopefully, because the keyword is produced, there's more entropy when you go out than when you went in. So that is going to be what we'll do. For S1, right? For S1, we just want to see the water part, literally SF, right? That means that your S1 is going to be, where should I write S1? Here. 1 point, what is that again? 7391. 7391 kilojoule per kilogram Kelvin. S2 will be a bit more difficult, but it's still manageable because the thing now is that S2, state 2, is now a two-phase mixture, aka it's now affected by quality. So we can just plug in the value that the formula that we know. SF plus X2 times SG minus SF. That will give us, what is this? SF of this is 1.1925 plus 0.0929 times, what is SG? 7.4791 and then minus 1.1925. That means that our S2 is going to be 1.1925 plus 0.929, 7.4791, 1.1925, 1.7765. 1.7765. So as you can see, the entropy in state 2 is just a little bit bigger than the entropy in state 1. That means that entropy was produced. The thing now that we need to do will be, oh my goodness, this is not the correct unit, is to get the correct unit. I would have given you guys a plus point if if you spotted that the unit here should not be in kilojoule per Kelvin, it should be in kilowatt per Kelvin. The thing about this is that kilojoule per Kelvin is only valid when you are doing this in a non-flow system. But this thing is flowing. This is a steady flow system we are talking about. So if you think about S, which should be m dot s, let's look at the units. This should be in kilogram per second times your S, which is in kilojoules per kilogram Kelvin. You will see cancel, cancel, and you will see kilojoules per second or kilowatt per Kelvin. Oh well, it seems like no one got it naman. But someone did get this answer correctly. I remember the answer here being 0.0155. Something like that. Let's just compute it right now. Right? The amount of your entropy that was produced is just going to be out minus in. S2 minus S1. Right? 0.4168. This will be in kilogram per second times 1.7765 minus 1.7391. This is in kilojoule per kilogram Kelvin. We go cancel, cancel. Oops. We go cancel, cancel. We will have 0.4168. Oops. 1.77 what now? Sorry. 1.7765 minus 1.7391. There you go. 0.0156. 0.0156. This is supposed to be kilowatt per Kelvin. This is your answer for number 13. Okay. Delta S is 0.0156 kilowatt per Kelvin. That is your numbers 11 to 13. And the last thing will be this part, number 14, right? It is an asterisk because I think I'm deeming that this is pretty difficult, right? Unless you have some training, I don't know, right? Two reversed Carnot cycles. So we're talking about ideal, right? Ideal circumstances here. Two reversed Carnot cycles are attached such that the first cycle absorbs heat from a source temperature of TA. From a source of temperature TA and rejects it to a sink of temperature TB. If you're already confused, you might already want to just try and draw this thing, okay? Let's try and draw this. Let's label it cycle 1, right? This is the first cycle, right? They say that this is supposed to absorb heat, right? Let's say this is your QA1. QA1, right? And it absorbs it at a temperature of TA. And then it rejects it to a sink of temperature TB, right? There you go. And then this heat at this temperature TB is then completely absorbed by the second cycle. So, oops. It won't hold. There it is. Oops. There. This amount of heat now, all of this heat is now absorbed, completely absorbed by the second cycle, and then rejects it to a heat, rejects the heat to a sink of temperature TC. Okay. If the coefficient of performance of the first cycle is 3, right? COP of this first cycle is 3, and the COP of this second cycle is 4. Tama ba? Yeah, the coefficient of performance of the second cycle is 4. What is the overall coefficient of performance of the combined reversed cycle? We're talking here about coefficient of performance. If there's nothing specified about it being cooling or heating, it will default to cooling over coefficient of performance, right? I would have said performance factor if I were talking about heating, okay? And the appearance of this might mislead people into thinking, I don't know, it might be like some very exact number, but the answer here should be COP overall is just going to be 1.5. Right? We'll find out how this is the case, but in this case, honestly, you don't even need to care about TA, TB, and TC. Right? Okay, right? That might seem intriguing. Like, why would I not care about these things, right, when they are specifically given? Well, not every piece of given information is going to be useful. So let's see how I do it, right? This is how I thought about it. Let's first consider just this first cycle here, right? This first cycle, it has a COP of 3. Right? What does COP mean again? Just for jogging your memory, your COP corresponds to basically how much heat you manage to absorb divided by the amount of work that you put in. If it's 3, then that means your heat, the amount of heat that you absorb, from me is going to be 3 times the amount of work that you put in. What does this mean? Literally, this cycle right here needs to have some work put into it, right? Let's just call this work 1, and same way, let's just call this work 2. Okay. Now, if the COP of this is 3, and the amount of work I put in here is 1, then it makes sense that because the COP is 3, the amount of heat that it will absorb is 3. Hopefully that's no big kind of a logical jump. And because energy is conserved, what goes in must come out. That means that if 1 and 3 go in, what must come out is 4. Okay? And then because of the second cycle, right, the COP of the second cycle is 4, right? 4. The thing about this now is that, wait a second, if I manage to pull in 4 units of heat, how much work do I need to put in? Basically, if we try to do this again, this is 1. And therefore, 4 and 1 go in, therefore 5 must go out. And now we're almost done. Right? If we were to look at this thing, right, from a bird's eye view, if we look at the overall coefficient of performance, basically the coefficient of performance of this whole box right here, right, we will see that if we manage to simplify things, right, this overall cycle, right, this overall reverse cycle, what happens is that we manage to absorb 3 worth of energy, and then how much work do we put in? I put in 1, I put in another 1. And then what comes out of here is 5, which makes sense, but the only thing that we need is the COP of this whole cycle. The COP overall will be, right, the amount of heat you manage to suck out divided by the amount of work that you put in. How much heat did we suck out? We sucked out 3. And then how much work did we put in? 1, and then another 1. 3 over 1 plus 1 is your 1.5. That is how I did it. And I understand and I am very proud of the people who just went in head first and who manipulated the equation of, right, COP is equal to TL over TH minus TL, right? Thank you for doing this, right? Thank you for stretching your brain, right? The thing is, of course, that things like this, right, of course, are not always going to be very perfect in their numbers. So if you want, you can try this. You can try this technique out. Try it with I don't know, letter I don't know, letter A and letter B. Tell me what the COP of the overall cycle is if your COPs 1 and 2 are A and B respectively. If you've managed to get to this video, to get to this part of the video, and if you manage to solve this and then send the answer to me via Canvas message, I will up your score by 5 in your diagnostic assessment. If you're still watching, of course. That is the overall COP, and that is how I solved number 14. Right? Of course, I think you guys can also solve this in your own way, right? If you continually manipulate that COP value. Okay? I suppose that's it for now, for this case, right? That's it. So that is my diagnostic assessment. I hope you managed to review, at the very least, what has happened over Method 1, Method 2, maybe a little bit of Mehetra, although I don't think we'll use Mehetra for this one. I hope that was enough of a review for you guys. I will see you soon.